To Is451. Today we will take a look at chapter 5, which is making connection efficient is through multiplexing and compression. I'm Professor Jalani. We'll be talking about this topic. So let's jump straight to it. As you all know, most medium can carry one signal at any time. Okay, for multiple signal, okay, in order for it to be able to be transmitted, it has to be subdivided. Here we take a look at the difference between frequency division multiplexing, time division multiplexing, and code division multiplexing. The first one is frequency division multiplexing. Here you look at the diagram. For example, a radio station has several different frequency to be transmitted. For example, SoundCloud channel 104.7 top 10 hits. That's what I listen to. Okay. So the demultiplexer separates the signal technically. Right. Also, as for in the IT world, analog signaling is used. Okay, in older system, more into legacy system. Okay, these are technically older techniques. And the diagram you see here, we have different channel 1 to 4 at different frequency. Right. Next, we take a look at time division multiplexing. Here they share of the same transmission, where it's divided into two forms: synchronous time division multiplexing and statistical time division multiplexing. Let's take a look at the first one. As for I look at the diagram here, we have device A to C, where, for example, the cache register is trying to communicate with the server, and here it's like a round robin. It will loop from device A, B to C and back to A again. Also, we can find this example in telephone system where they use T1 and SONET. So if in order for the device to generate data faster, okay, so it has to be sampled quickly. Okay, if there is no transmission, okay, the system will still include an ideal data bit. In this case, you look at the diagram, D is idle, so they still put a data user in, because it's part of the loop. Here we see the bits form, A to D. Okay. We have the byte type followed by the synchronization bit, 1s and 0. As for T1 multiplexing, extreme and continuous frame with a 24 voice grid telephone line, okay, plus one sync. Okay. As mentioned in the diagram, that's why the T minus 1, N minus 1. Okay. So all 24 channel is combined into one channel, totaling 1.5 megabits per second. Next, we have SONET multiplexing, similar to T-1. if you look at the frame layout, we have the section overhead, line overhead, and path overhead data. Okay. So one frame is 810 bytes. Bits is 6,480 bits. Okay, as compared to T1 frame. Okay, with 24 bytes. The layout is different. Yeah. As for next, we take a look at statistical time division multiplexing. It's only for active workstation only. So if the workstation is not used, it's not wasted. This is more efficient. On the sample data, we have here data of A and C. Right? So those not used are not being wasted. This is how they identified. For variable data, okay, a line is also included. See more precise packet layout. But we have the flag control, the address of the packet, length, the data, and also by the flags and FCS. Next, we take a look at wavelength division. So it's the same thing. In this case, using fiber optic, and wavelength laser, called in this case lambdas, transmit the signal, and it combines 30 to 50 wavelength into one fiber. Okay. And look at the diagram here. We see, for example, ATM, OC-12, OC-1, and frame delay. At different megabits. It's being transmitted over the fiber optic. As for next, multitone, is usually used in DSL, okay, digital subscriber line. So, like for example, you have 256 subchannel with 660 kilobits. Okay. The diagram here we see 256 stream from a splitter to a multiplexer. So it's quite susceptible to noise, and it will slow the process. As for code division, okay, multiple access, okay, it's basically transmitting multiple signals same time, 64-bit, ones and zero, binary, with near plus minus 64. Next we have 8-bit code. Here the example we see mobile A to C. Assume mobile A sends 1 and B sends 0 and C sends 1. So signal code 1 minus chip equals to plus n volt, and 0 chip minus n volt. Okay, so we have 3 signal, right? The interpretation is 1 is plus and 0 is negative. And having said that, so the substation received by the base station is plus negative 1 plus 1. This is basically the summation of all three signal. So next slide, we see the signal received plus negative 1 plus 1, and bombard A code is plus 1, and the result is negative 1, for example. The sum of product is plus 8. So the decode rule for result near plus 1 binary is 1. So initially we have the signal and is converted to ones and 0. Sorry, 1 minus 1 and plus 1, and it's been total and combined and being transmitted and decoded at the other side. And this is happening at a split second. Let's take a look at comparison. All the different type: frequency division multiplexing, synchronous division multiplexing, wavelength division multiplexing, discrete multitone, and code division multiplexing. These are basically, as for frequency division multiplexing, some of the advantages: simple, popular with the TV. Disadvantages are noise, bandwidth. Synchronous time division, is digital. Also waste bandwidth. Sorry about that. Apologize for that. And next we have statistical time. It's more efficient. With varying size, but it's more complex. Wavelength, very high capacity over fiber, cost and complexity. Discrete multitone, capable of high transmission. Noise. Code division multiplexing, large capacity, complexity when using wireless. Next, take a look at loosely and very loosely. Source lossless versus loosely. These are basically compression technique. Most signal are being compressed to increase efficiency, and lossless is technically a data uncompressed, and it returns the original data. Loosey is uncompressed data, but you might not get the original. So where is it applicable? You will use lossless in financial file, which you would require the same type of data, in order to get back the original. Because it's quite crucial. Loosey is you will find it in video, image, audio file, where sometimes when you receive there is some noises. Some of the lossless example, Huffman code, run length, FZ compression, FLAC. As for loosey is MPEG-3, JPEG, and MP3. Let's take a look at the example here. This is lossless. The run length replaces zeros with a count of how many zeros. Here we have 14 zeros, followed by 9 ones. And now replace each decimal with 4-bit binary, okay, from the 0 to the number, and then it's being converted by 4-bit binary. So if you have a code larger than 15, you need to 2 consecutive bit. Okay. First is binary. For example, 15 is 1111. Here we have 20, which is 1110101. Okay, where basically it's a sum of 15 and 5. For loosely compression, it's used in video and audio. Okay, so to take advantage of the human ear, where we are not that perfect to pick up the error. In audio, especially MP3, okay, is used. So there are times when the human ear are only able to detect louder sound as compared to softer sound. Here, the louder the sound, for example, if you are listening to a radio, to MP3 in your earpod, and while walking through the construction, you will hear the construction much clearer than the music. Video compression, okay, either moving or still. Okay, video is very small, okay, as compared to still image, where the frame is quite small. Okay, let's take a look at the framing first, to have a clearer understanding. Okay, the first frame we have on the left here, and second frame. As we compute together, we have the difference. Okay, that's the video compression technique. Next we have MPEG, or motion picture expert group. This is created with small differences of frame. Okay, it compresses both video and audio. Image compression is RGB, red, green, and blue. Okay. These are the values, and for example, you have using the 3 colors with 8 bits, so totaling 24 bits, 2 to the power 24 colors. For 640 to 480 pixel, you have here 24 bits multiplied by 640 multiplied by 480, which is 7 million bits, okay, to need to be compressed. So the higher resolution of the image, the higher the bits. JPEG, Joint Photographic Expert Group. Okay, compress still image loosely, 3 phases. Okay, discrete cuisine, transformation, DCT, quantization, and runtime encoding. Step 1, okay, the image is divided into series 8 by 8 blocks. Okay, if the image was original 640 by 480, here we have 80 blocks by 60 blocks. Black and white we have 8 by 8, 8 bit 0.02255. So if for color we have 24 bits, 8 bit for red, 8 bit for blue and green. Let's take a look at the blocks. 640 by 480 here, divided by 8 by 8 pixel block. So technically your picture is divided into individual blocks, subdivided, and each block, okay, is being computed. So what does it do? Okay, with 8 by 8 matrix, okay, it's called spatial frequency, okay, and with little fine detail such as P matrix, okay, is being used. Okay, and also T matrix is with many non-zero values. Let's take a look at the next slide to be more precise. Here we have the overall picture is being divided into blocks. In the first block we have 120 P matrix, and in T matrix after the cosine transformation, the top left hand corner is 652. Okay. Stage 2, basically for the human eyes, you cannot see the difference in color. Okay, and T matrix is divided by 10. Okay, and here we divide T matrix by 10, the same figure. Okay, will have the value above. And this is the original Q matrix after the cosine. Okay, then next we go to step 3. It's run through the rung length encoding, and you see here how it's been run from top left hand. It will go like a zigzag motion to be transmitted. So how you get it back? So on the other receiving side we have decoding. Basically the reverse process, you undo the run code, multiply the Q matrix by U, okay, and yielding T matrix, and not forgetting the cosine of P matrix back. And for example, here we have Bill's Market has 10 cash register at the front of the store, and wants to connect all cash register together to collect later transaction. List some efficient techniques to link the cash register. Some possible solution: you connect each cash register to a server using point-to-point. Okay, transmit the signal of each cash register to the server using wireless transmission, and combine all the cash register output using multiplexing and sending the multiplex signal over the conducted medium. Okay, these are some of the real case scenario that you might face in the real life. Okay, then that's pretty much it. If you have any question, please email me or make an appointment to see me in the office. Okay, stay safe and thank you very much.